Hello Algebra 2, and we are now venturing forth into territory that is not covered by your book, but should be covered by your book. It was in our last Algebra 2 book, and they are actually important identities. The one you're getting today are actually some of the most used identities we have. These are the double angle formulas. So again, we have here, it's just a matter of, writing something two different ways. So if you see sine 2 theta, that is equivalent to 2 sine cosine. Cosine 2 theta actually has three different identities depending on what you need to do. And then your tangent 2 theta is 2 tangent theta over 1 minus tangent squared. And we are going to actually derive these because we can use the sum and difference formulas that you got in the last lesson to derive these. We're doing the sine and the cosine one below, so I'm just going to do the tangent one up here. So what you guys looked at in the last lesson was an identity tangent A plus B. Well, what if A and B are the same thing? So notice here, this is another way to write tangent 2 theta, because theta plus theta would be 2 theta. I can use the sum, our components that we looked at in the last one to expand this. This would be tan theta plus tan theta all over 1 minus tan theta times tan theta. And this is basically how you would derive all of these. So on top, I have tan theta plus tan theta is the same thing as 2 tan theta. And on the bottom, tan theta times tan theta is the same thing as tangent squared theta. So that is where that identity comes from. All right, let's look at one of the uses of these. So it asks us again to find the exact values of sine 2 theta, cosine 2 theta, and tan 2 theta when you are given this information. Now, just like in the examples we did in the other video, this information is how you would set up your triangle, one of your bow ties. All right, so let's go ahead and do that first. So we're going to be looking at the first quadrant because that's 0 to 90 degrees. So I'm just going to draw a first quadrant, draw a triangle here. And that means theta is coming out of the origin because this is 0 degrees, this is 90 degrees. And it tells us cosine is 3/5, so that's the adjacent over the hypotenuse. So we have a 3, 4, 5 right triangle, which always makes things very friendly. How would I find that if I didn't know it? I'd have to do Pythagorean theorem. All right, find the exact values of sine 2 theta. So we take your sine 2 theta. First thing we do is expand it with our identity. So sine 2 theta is the same thing as 2 sine theta cosine theta. So now that I don't have a double argument, I just have theta, not 2 theta, I can look to my triangle and I can substitute sine theta is opposite over hypotenuse. So I'm going to substitute this with 4/5. Cosine theta is adjacent over hypotenuse. And so this all simplifies out to, let's see, we got 12 times 2 is 24 25ths. Okay, now we're going to do, it wants us to do, we did sine, now we're going to do cosine. So cosine 2 theta. Now here you have lots of options because you have three different, and my recommendation is if I'm given information that has to do with just cosine, I'm going to use the identity that just has a cosine in it because then I don't even need to draw the triangle. So 2 cosine squared theta minus 1, and then we're going to substitute. So 2 times 3/5 squared minus 1, and then we're going to simplify that. So this is going to equal 2 times 9/25 minus, and since I have to put these together, I'm going to rewrite 1 as 25 over 25. I apologize. That is my dishwasher in the background, so I hope that's not too distracting. So then I have 18 minus 25, which is a -7 over 25. And that would be the equivalent for cosine 2 theta given our information that let us draw the triangle. All right, and then the last one, they wanted us to also find tangent 2 theta. So we only have one identity for that. So tangent 2 theta is your, I'm going to write it down here, 2 tan theta over 1 minus tangent squared theta. So we will substitute into that. 2 times tangent is opposite over adjacent, so this will be 4/3. And then 1 minus 4/3 squared. Whoop, and almost dropped my iPad there. Now we start to simplify this. So on top, this is like 2 over 1. I have 8/3. And on the bottom, I have 1 minus 16/9. So fraction over fractions again. Yeah, the tangents are always a little more not as friendly. So let's do this though. I'm going to rewrite 1 here as 9 over 9. So I have 8/3 over 9 minus 16 is a -7/9. And we can invert and multiply so that I have 8/3 times 9 over a -7. 3 goes into 9 3 times, and I end up with a final answer of -24/7. And remember that tangent is the ratio of sine over cosine. So if you look at what our answers, final answers were, if I made a ratio of 24 over 25 over -7 over 25, your denominators would cancel, and that would leave you with -24/7. Just a fun fact for the day. All right, verify. So now what we're going to do is derive our sine 2 theta like we did with tangent. So we know that sine 2 theta equals sine theta plus theta, because that equals 2 theta. And now we'll expand that. So that's your sine theta cosine theta plus, it doesn't matter what order I write them in since they have the same argument, sine theta cosine theta. So I have a sine theta cosine plus a sine theta. How many sine cosines do I have? I have 2 of them. That is as easy as that derivation is. All right, now let's look at the cosine. So the first thing I want to do is just derive our cosine. So we know that cosine 2 theta equals cosine theta plus theta, basically the same process. We expand this, so this is going to be cosine theta minus sine theta, and that gives us cosine squared theta minus sine squared theta. All right, so that's one of the identities, and this wants us to derive the other 2. And the way you do that is using your Pythagorean identities. So a little reminder here that, remember, cosine squared theta plus sine squared theta equals 1. That was from 9-7. I believe you got your Pythagorean identities. Okay, so let's work this out. Let me rewrite my cosine squared theta minus sine squared theta here. So what I'm going to do for the first one is I am going to, remember you had a little grid where we isolated a different variable each time. So if I isolate the cosine squared, that equals 1 minus sine squared. And if I isolate sine squared, I get 1 minus cosine squared. So what we're going to do is a little bit of substitution. So let's do cosine squared first. So I'm going to substitute cosine squared with 1 minus sine squared. And then I still have minus sine squared. So putting it all together, I have 1 minus 2 sine squared theta. And that gives you that last identity up there. Let's do the same thing again. Oops, lost my pen. Here's cosine squared theta minus sine squared theta. This time, we are going to substitute in for sine squared. So we have cosine squared theta minus, in parentheses, 1 minus cosine squared theta. So we can distribute that negative. That gives me cosine squared theta minus 1 plus cosine squared theta. Putting it all together, I've got 2 cosine squared theta minus 1. So my two little lines always just kind of represent. So that was the identity there. Okay? All right, so now we're going to get a little bit deeper into solving trig equations. And again, there's no one way to do these, but there are strategies that can help, just like you have strategies that can help with proving identities. And so I'll try and emphasize that. One of the things you do want to do is always manage to set the equation equal to 0 if possible. And especially if you have more than one factor, then you can set each factor equal to 0. So we have sine 2 theta equals 2 cosine theta. Well, you know, it's like, I have no idea. So what we do, you'll never be able to solve a trig problem if your argument, your 2 theta and one is a theta, if they don't have the same type of argument. So we're going to expand. Sine 2 theta, we're going to use our identity. That's 2 sine theta cosine theta equals 2 cosine theta. And as I said, we want to set this equal to 0. So 2 sine theta cosine theta minus 2 cosine theta equals 0. Now, the strategy I'm going to use here is, I notice, and we actually talked about this when we were doing just the identities as well, you have a GCF, you have a common factor that we can pull out. Actually, I can pull out the 2 as well. So I'm going to pull out 2 cosine theta, and I'm left with sine theta minus 1 equals 0. So now that you've got it set all equal to 0, it's like a quadratic type of equation where you set each factor equal to 0. So we are going to look at solving 2 cosine theta equals 0, because that would make the whole thing 0, or sine theta minus 1 equals 0. And this is where you're going to want to use the unit circle that we have down below. So first off, let's kind of simplify this. I can divide through by 2, and really I'm looking to solve, I'm going to kind of put it over here, we're looking to solve where does cosine theta equal 0. In other words, where on the unit circle do you see an x coordinate? Because remember, cosine goes with the x value, sine theta is going to go with the y value. So where do I see an x value of 0? I see one here, and I see one here. So that tells me, and since this came to us in degrees, I'll give my answer in degree. So theta will equal 90 degrees or 270 degrees. And basically you're just looking around the circle for that particular x value where it equals 0. Now let's look at our sine equation. we have sine theta minus 1 equals 0, which is the same thing as saying sine theta equals 1. So where does sine theta equal 1 is like asking where are the y values equal to 1. And I only see one possibility, which would be right here, which is also at 90 degrees. So my answer is theta, we usually like to write it as a set, is 90 and 270. It's okay that there's the repeat. It's still the same solution. That would be your answer right there. All right, so it's really relying heavily on looking at your unit circle. Okay, so we're going to go on to the next one, which will have a different. So let's look at this. Cosine theta tan theta minus sine squared equals 0, again, for one revolution around the unit circle. So we look at this, we don't see a GCF. So one of my suggestions, kind of like doing your identities, let's try and simplify this down, see if we can simplify it. I am going to try and put everything in terms of sine and cosine. So tangent, remember, is sine theta over cosine theta. So that's all I did was rewrite that as it's the ratio of sine and cosine, minus sine squared equals 0. Okay, well that's nice, but it lets me cancel this out. And now I am back to the same strategy we used in the other problem because I do have a GCF. I can factor out sine theta, and the first place I have a placeholder of 1 minus sine theta equals 0. And now that we've made it into a product, I'm going to set each one of these equal to 0. So where does sine theta equal 0? And where does 1 minus sine theta equal 0? Which is kind of like asking where does sine theta equal 1? All right, so we have two different things we're looking for. So where does sine theta equal 0? Again, that's the y values. So I see a 0 here, and I see a 0 here for the y values. So that would be at 0 degrees and at 180 degrees. And where does sine theta equal 1? Well, that was the same one we had up before. So that was, I should say, theta equals 90 degrees. So in this case, we have three answers. We have 0, and we tend to write the answers in sequential order, numerical order, however you want to say that. And that is your solution. You do have a check. You could plug in 0 and 90 and 180 successively into those equations, and you would get back. But notice we haven't even touched a calculator, so this should all be done just by looking at your unit circle. All right, let's try one more. So we don't necessarily want that solution. We have 2 sine theta equals negative rad 3. All right. Well, this is one where you're not going to necessarily set it equal to 0 because I do want to isolate my sine because that's what I'm trying to solve for. So sine theta equals negative rad 3 over 2. That should look like a familiar ratio. And again, we're going to go around the circle. Now, sine, remember, represents the y values. So y values are negative down here, below the x-axis. So we're looking for a y value that's a negative rad 3 over 2. There's one there, and there's one here. So they both have reference angles of 60 degrees here. So that's going to happen at theta equals 240 degrees, and again at 300 degrees. And you know what? That is your answer. So I hope this goes well, and nice application of various properties we've looked at.